Well, hello again. I hope everybody's doing well. This is now we're still continuing with chapter 2, looking at the lecture PowerPoints. Now we're on the second video. This little group of slides is going to be concerned with how atoms react with other atoms and why that is. So we start off again just reviewing. We talked about how um, chemistry is the study of matter, and matter is everything that has takes up space and has mass. And we talked about how it is organized in elements. Atoms are the building blocks of all things, and so these elements are specific categories of atoms. And so this was set up, the periodic table, and we organize them by what we call the atomic number. The atomic number is simply the number of protons in that element. And how in an ideal world, the same number of electrons would be present, causing it to be neutral. But we're going to see in this video how that changes in the real world. And so we also talked about isotopes. This neutron we can have the same atomic number, the same element, but we could have different numbers of neutrons, which we find the atomic mass is the number of protons plus the number of neutrons. So if I know the atomic number, I know the mass number, which is telling me the atomic number is telling me the number of protons. And if I know the mass number, it's the number of protons plus neutrons. So I can figure that out. If I have gained or lost a neutron, that is considered an isotope. So now we're going to look at the electrons. So again, we're looking at the atomic structure. We have something called a nucleus. This is where the protons and neutrons are located. And then outside of it, we have these little orbits, these shells they're called, that are where the electrons are found. Now they are organized in a way where they have limited seating, so to speak. And so if you take more advanced physics or in physics and chemistry, you're going to look at these, and these are very complicated. They're generally called clouds or more specific because electrons, because as we said in the last video, they have they don't contribute to the mass of the overall atom. That's why the mass number is just simply the addition of protons and neutrons. But they're kind of these weird things that I won't get into that quantum physics type stuff, but they are almost virtually massless. But they're found in these little areas that we'll call shells for us in here. Now, the way that atoms combine, if two atoms combine chemically, that is called a molecule. If in that molecule it is two or more types of atoms, that is specifically called a compound, or can more specifically be called a compound. So O2, two molecules of oxygen that are bound together, is a molecule, but it is not a compound. H2O, which we call water, again, forgive me, I'm using the mouse pad to try and write with. While H2O is also a molecule, it can more specifically be called a compound because it has two different types of atoms, hydrogen and oxygen. Now, the molecular formula, again, is how we look at these. You just write them out. This is how we're going to look at them in here in general. We're not going to get into a lot of the deals with how we write out or draw out molecular structures. But the main one is a molecular formula, which just tells how many, it doesn't say how they're organized, it just tells how many of each compound or each element is in the compound. So for instance, glucose has a molecular formula of 6 carbons, 12 hydrogens, and 6 oxygens. But you'll see that that's pretty much the same molecular formula for all simple sugars. So the way to tell the difference between glucose and fructose would be to actually look at the way it is drawn out or how it's organized. But that's above our pay grade right now. We're just looking at these to get our feet underneath us, so to speak. So this is a picture of showing how these on this side, while they are molecules, when they combine, now these now can more specifically be called compounds because I have hydrogen and oxygen bound together. Now, chemical bonds are how atoms combine and interact with other atoms. And there's two really main ways that they can do this. One's called ionic, one's called covalent. And we're going to look at how this works. But first, we need to see how electrons work. So electrons of an atom occupy regions of space called electron shells, which encircle the nucleus. That's what we were just looking at. Now, we're going to see that atoms can be very large, all right? But we're not going to deal with those. The ones that we deal with mainly in here are going to be below having an atomic number of 18. And so these in particular have a very distinct pattern, but even when you get larger, you'll see that the pattern's the same, only it just like multiplies it. But the way it's set up is I have my little nucleus, and then I have my first shell. That first shell can hold 2 electrons and no more. Once I get that third electron, now it spills over into the second shell. And the second shell, as well as the third shell, can only hold 8. And as soon as it's full with its 8, the ninth one, or which would end up being the 11th one total, ends up spilling over into this third shell. And so the first shell, which is and it has to fill in from the innermost and work out. So the first shell holds 2, the next 2 hold 8. And so there is a rule, it's called the rule of octets, which means the rule of 8, and that kind of is how atoms are kind of, and their electrons are functioning in this rule of 8. It always wants to be full, and the first one is full at 2, the second 2 are full at 8. All right. Now, if we went back to, and I said this on the previous video, when we're looking at the table of elements, if you knew the atomic number, you would also know the atomic number, which is telling us how many protons there are. If I know that, I know in the ideal world, I'd know how many electrons there are. And I compare the ideal world to this, the Christmas card analogy. You know, if you see a family and everybody's on the front of the Christmas card and they're all dressed up and they all look nice and they all look like they're getting along, and you give the but then you say, well, I know those people and that's not like them. They're a total mess. It's like the Tasmanian devil. Just, you know, a mess of chaos going around. There's two different views. When we look at the Christmas card or the idealized view, I know that if I have only one proton, this would be the atomic number 1, that means I have 1 electron. If I have 2, I have two protons. If the atomic number is 2, I have 2 protons. That means I have 2 electrons on the Christmas card, and so forth. If I have 3, if the atomic number is 3, that means I have 3 protons, and that means that in the ideal Christmas card world, I have 3 electrons. So if I told you that sodium has an atomic number of 11, you would know that it has 11 protons, and that means that in the ideal world it has 11 electrons. And if I could do it like this, if I tell you that then it also has 12 neutrons, you should be able to tell me that the mass number or atomic mass is going to be 23. All right, now again, this book is going to kind of confuse you, keeps throwing atomic weight out, but don't worry about that. These two up here are the main ones that I'm concerned about, the electrons and protons, and really the electrons, right? So if I did this, and it's already here for us, but if I say that the atomic number is 11, and so I put it in the 11 electrons, what you would find out, I'd get 2 in the first shell, 1, 2, and then I would get 8 in the second shell, but I would count, 3, 4, my dog's trying to count for us, 5, 6, 7, 8, 9, 10. And so there's 10, I'm counting off the total number, all right? So we had 2 in the first shell, 8 in the second shell, so that's 10. And we know we have 11 electrons, so this 11th electron hangs out here by itself in this outermost shell. Now we're going to see in just a little bit, the outermost shell is called the valence shell, and electrons in the valence shell are called valence electrons. All right, so I hope, again, following through. As soon as I know the atomic number, I know how many protons, and then I know ideally, how many electrons. Since I know they fill from the innermost shell working out, the innermost shell takes 2, the next 2 use 8. So if I have 11, 2 on the inside, 8 in the next shell, that means there's 1 left over in the outermost shell. So that valence shell has 1 in it. Now, what happens is, and unfortunately, I should have continued with that slide. If I have, so we got this here, let's say, I'll try to draw it here. This is my bad version of that sodium that we just looked at, 11 electrons. So I'm just going to leave this 11th electron way out here. I'm not going to go through and put all the ones in the 2 innermost shells, but we have that last electron, that valence shell electron. Now, all atoms want their outermost shell to be filled. That's the driving force of all atoms. They want it to be filled. And so if I have something like sodium that only has 1 electron on the outermost shell, it is going to kick this to the curb. Because what happens once I get that electron out of there, now I can get rid of that last shell. But the problem is, since I got rid of this electron, it is now gone. That means I have 1 more positive charge than I have negative, because now I still have 11 protons, but now I only have 10 electrons. So this has a positive charge, a positive 1, which is just denoted usually as having a plus. This is an ion. Now I could have done it the same way, and let's say that this has a atomic number of 9. So let's say it has an atomic number of 9. What ends up happening is I take 2 for the innermost. That means there's 7 left. So that means I have this 1 empty vacancy here. And instead of kicking an electron out, I'm going to pull an electron in. And at that point, I have 1 more electron than I have protons. So this would end up being a negative ion. And so I put it positive, sorry, I'm not going to go through a -1. There we go, it worked out. These are called ions. All an ion is an atom that has gained or lost an electron to become stable. It has a charge now, and it can be positive or it can be negative. Positive charged ions are called cations. Now, remember, if it is positively charged, and this is a weird thing, if it is positively charged, that means it lost an electron, right? The electron that got kicked to the curb. Now, if I have gained an electron, right? So let's say I've added an electron, that means I've added a negative charge. So now this ion is a negatively charged ion, right? Because it has gained an electron. This is called an anion. Now, these two, this positive and negative, can then act like magnets and attach to each other with no sharing, just simply by the bond, the electric impulses from those. And we call that an ionic bond. It is a bond where the charge attracts them. Again, they're like magnets. Now, there are easy ways to remember a cation is the positive. A lot of people say, well, cat people are positive people. Now, I'll leave my opinion on that. I'm a dog person necessarily, but I'm not going to say I dislike cats. But anyway, just jokingly, I'm like, eh. But the way that I kind of believe that if you understand why words are called that, it helps in more than just one way. And memorization just ends up meaning you got to keep learning things. In metabolism, which is a concept we talked about in chapter 1, metabolism is the sum of all of the chemical equations going on in your body. Some things are breaking down, some things are building up. We're going to see this in the next chapter, in the next couple of videos. Mechanisms that take a big molecule and break it down, or it doesn't even have to be a molecule, something large, but in our body we're talking about molecules. So if I'm talking about AB, a molecule that is AB, and I do something to it and it breaks it down to smaller components, you know, A plus B, right? This is taking something large, the AB, and breaking it into smaller things, A and B. This is called catabolism. Right? Catabolism has its root in the same thing as catastrophe. It's breaking things down. And so because I have lost an electron, the atom got smaller. So we refer to that as a cation because it has gone through catabolism. If I was to reverse this equation and take these two small things and make a larger substance, that is called anabolism. And most people, you might have heard of the term, the steroids called anabolic steroids. They're called anabolic steroids because they build you up. An anabolic mechanism takes small things and makes larger things out of them. And that's why we call this an anion, because I have added an electron, so it has gotten larger, and that's why we call it an anion. And again, you know, not trying to just constantly say these little things, but I'm telling you, if you can get a hold of why things are called what they are and understand the mechanism, it will help so much in so many things. But whatever the case may be, cations are positive, anions are negative. Cations have lost an electron. Because they lose a negative particle, that makes them positive. That's a hard thing to think because we don't think of it in directions like that because we don't deal with negative things very often. An anion is a negatively charged ion because I have gained an electron. All right, so these two things, these charged ions, can combine and form what we call ionic bonds. So this is showing them, right? So again, this is sodium with 11 protons. That means I've got one left over in its valence shell. Chlorine has 17 protons, which means if I do the math, two in the innermost, 8 in the next, which makes up 10. That means I have 7 in that third valence shell. That means I have this one empty space. That is dying to have an electron. So this one kicks the electron out. The electron comes over here, forms its little spot. This, because I've lost this electron, this becomes a positive ion that we call a cation. This, because it gained an electron, becomes a negative ion that we call an anion, because again, it added to it. And now these charges will attract each other. And then we have salt, basically, sodium chloride. All right. Again, the way it's set up, there's no actual sharing. The bond is simply the electromagnetic force between the positive and negative charges. And again, I hope all of that makes sense. Ions, again, are simply atoms that have gained or lost an electron. If it has gained an electron, since electrons are negative, that means that there's one more negative than positive, so they are a negatively charged ion, and they're called, since I've gained an electron, they're called an anion. If I lose an electron, that means that I have one more positive, I got one more proton positive than I have electrons negative, so they are positive. And since I've lost something, that means I got smaller, so we call that a cation because it's gone through catabolism. And it's all about having their outermost shell, that valence shell, full, whether I'm gaining things to fill it or losing things to drop down to the next level, which then is full. That's how atoms react in the real world. That's how it goes from the Christmas card, which is the periodic table, to the real world, which is our body. And I hope that makes sense.